Good day, everybody. I want to talk about matrix multiplication and transpose of matrix, and this is one of the topic we are dealing with in algebra. First, let's look at the definition. Suppose I have a matrix A, which is n by n, and I have a matrix B, which is n by p. The question is, how do I compute A times B? Just to recall, in class we dealt with when does it make sense to compute A times B. So A times B will make sense, and this is what we call compatibility rule. If I have n by n matrix and I'm multiplying it with n by p matrix, notice here that the column of A, which is n, is exactly the row of B, which is also n. That is when it makes sense to have A times B. And the resulting matrix will be of size m by p. Okay, so again, keep it in mind, you don't have compatibility rule must first be satisfied, otherwise it doesn't make sense to multiply two matrices. So as a matter of emphasis, if I want to multiply A by B, that is A times B, the column of A must be exactly the row of B. That's when it makes sense. So after this compatibility rule is satisfied, the question will be, all right, how do I do this computation? So I want to first look at a very simple way of doing that. Having in mind that we learn how to multiply matrix by vector. So now this is matrix by matrix. So the first thing is to decompose B into columns. And so B1 represents the first column of B, B2 represents the second column of B, all the way to the last column, which is BP. So imagine we just decompose B into columns, B1, B2, all the way to BP, since B has P columns. All right, once we do that, we then multiply A by B by multiplying A by each of these columns, using the idea of matrix times column multiplication that we did before. Again, just to remind you, the product AB is going to be M by P because N is the number of columns of B, and N is the number of rows of B. Now the resulting matrix AB will be, we have column 1, which is going to be AB1, column 2, which is going to be AB2, all the way to column P, which is going to be ABP. Just to write it out clearly, so if I have A times B and I've represented B in column form this way, so that A times B will be in this form, because this is now representing your B. And then all I need is to multiply A by each of these vectors, column vectors. So you will have A times V1, A times V2, all the way to A times BP. So this is one way to easily visualize how to multiply two matrices. As a matter of emphasis, be careful. It will change once we multiply B by A. If we reverse it, then A will be written as a column, in column form, and then we multiply B across the column. All right, so then we have what we call row column rule from computing AB. How does that work? If a product AB is defined, then the entry in row I and the column J of AB is the sum of the product of corresponding entries from row I of A and column J of B. This is actually very simple once we come to examples. So I'm going to solve some examples to illustrate this. All right, so in mathematical terms, so if I want to multiply A by B, ij entry of the product will be given as ai1 times b1j plus ai2 times b2j all the way to ain times bnj. All right. Again, I'm going to use this idea in solving some examples. All right, so let's look at some properties of matrix multiplication. Suppose we have a matrix A, which is n by n, and we have B and C with sizes for which indicated sum and product are defined. So we are assuming that the compatibility rule for multiplication and addition and subtraction and whatever, the rule is satisfied. So first, if I multiply A times the product of B and C, I can reassociate this into AB then times C. This is called associative law of multiplication for a matrix. Also, I can distribute from the left. So A times B plus C is actually A times B plus A times C. Be very careful of the position. We don't just change the position like we do in for real numbers. And then the same, we have right distributive law, which means from the right we multiply A. So BC all times A is B times A plus C times A. This is extremely very important to be very, very careful. So the B is the left distributive law, and the property C is the right distributive law. Again, R here is a scalar, so if I multiply a scalar times the product, I can reassociate this scalar in any way I like it. Of course, when you multiply the identity matrix with a matrix A, you recover the matrix back in either way, either from the left or from the right. All right. Another one is, again, I'm going to talk about it. When you multiply A times B, you do not necessarily get B times A. These two is not necessarily the same. The product AB may be completely different from BA. Whenever it is true, we say that A and B commute with one another. All right, so warning. The first one is that in general, A times B is not always equals to B times A. Be very, very careful with this. A times B is not always B times A. When it is true, I'm going to talk about that in my next video. Also, cancellation law do not hold for matrix multiplication. And what is cancellation law? If I multiply A times B, if I have A times B and I have A times C for real numbers, it means that B should be C. But for matrices, in general, it is not true that B is C. So A times B equals to A times C does not necessarily mean that B is C. And finally, if a product AB is the zero matrix, you cannot conclude in general that either A is 0 or B is 0. Remember that in college algebra, X times Y is 0. If X and Y are real numbers, X times Y is 0 implies that at least X or Y is 0. For a matrix, that is not always the case. There are non-zero matrices that you multiply together and end up getting 0. So that I multiply two matrices together and get 0 does not in general mean that either of the matrices is 0. All right, so let's look at some examples. I'm going to take this example to talk more about transpose and talk more about the products and the addition. So in general, I'm going to walk us through examples that cut across matrix algebra. So in this example, I have a matrix given to me, and this example is the first question on the worksheet. Matrix A is given as 2, -1, 4, then 3, 0, 5. By the way, this is 2 by 3 matrix. Just keep it in mind. And matrix B is given by -1, 3, 2, 0, -1, 4. Again, think about it. What is the size of matrix B? It's 3 rows and 2 columns. Matrix C, in the other hand, is 1, 0, 4, 2, 1, 3, -1, 2, 0. This case, we have a 3 by 3 matrix. And lastly, matrix D is -4, 2, 3, 1. And of course, this is a 2 by 2 matrix. Now, what's the question? The question is find, if possible. This is also to test whether you understand compatibility rule for matrix algebra. If possible, find A plus B transpose, B, A times B plus D, then C times A transpose, lastly, C times B plus A transpose. So I'm going to be looking at these 4 questions, and that will help us to explain what we've learned so far in terms of matrix algebra. Don't worry, I'm going to write whatever I'm doing. So let's start with the first one, A plus B transpose. Before we can do this, we need to find B transpose first. So B again is -1, 3, 2, 0, -1, 4, which then implies that B transpose will be, remember that transpose is row for column. All right, so the row of B is -1 and 3, so that becomes column here, which is -1 and 3. Then the second row is 2 and 0, so it becomes column here 2, 0. The last one here is -1 and 4, so it becomes row here. It becomes column here, which is -1 and 4 this way. That's how to find the transpose. So again, we just transform the row to a column. That's all you do when you do the transpose. Now, remember that A is A is 2, 3, -1, 0, 4, 5. The question is, so B transpose is now 2 by 3. A itself is 2 by 3. Remember that for addition of matrices, the size of the matrices must be the same. The size, you must have the same size for the matrices you are adding together. So in this case, it makes sense to have A plus B transpose. So who is A plus B transpose? A is given to be 2 -1, 4, 3, 0, 5. And B transpose, we got that to be -1, 2, -1, okay, 3, 0, 4. Remember that when we had matrices together, we had entries components wise. So this is the first entry here is 2. We add to the first entry here, which is -1. So 2 -1 gives us 1. The second entry here is -1. We add it to this entry. So -1 plus 2 is 1. Then the next one, A13, we add it to B13. That's 4 - 1, that is 3. For the rest, so the next one will be 3 plus 3, which is 6, 0 plus 0, which is 0, and 5 plus 4, which is 9. So that is A plus B transpose. All right, so let's go into the second question. Question B, that asks us to find A times B plus D. So we need to be careful here. First, what is A, what is B, what is their sizes, what are the sizes, and how are they compatible, the multiplication. So remember that A is let's just write the order here. A is 2 by 3. B is 3 by 2. And D is 2 by 2. So let's see whether what we want to do makes sense. First, A times B will be 2 by 3 times 3 by 2. This makes sense because the column of A, number of columns of A is exactly number of rows of B. And the product should be 2 by 2. So imagine that this cancel out this. So we will be left with 2 by 2. Now, AB plus D, does it make sense? It will make sense if the size of A times B is exactly the size of D, which is true because we just got that A times B is 2 by 2 plus D times the size of D is also 2 by 2. So definitely this makes sense. So we can go ahead and first find AB. So the goal is to find AB first. So who is A times B? A times B will be matrix A, which is 2 minus 1, 4, then 3, 0, 5. I want you to pay attention here when I'm doing the multiplication. So A times B, B will be minus 1, 3, 2, 0, minus 1, 4. All right, so I'm going to use row column rule here, which is take the first row against the first column. So we take the row against the column. That's the first thing. And we do the product and add entry-wise. So row I times column j. So 2 times negative 1 is negative 2 plus negative 1 times 2 is negative 2. Then we have 4 times negative 1, which is negative 4. Again, 2 times negative 1, the first one, the first column, the row here, the first entry in the row 1 times the first entry in column 1 for B. And we do the same thing for this one. So again, we'll have 2 times 3, giving us 4 or 6, minus 1 times 0, that is 0, then 4 times 4, that is 16. We are done with row 1. We go to row 2 and we do exactly the same thing. So that would be 3 times minus 1, that is minus 3. 0 times 2, that is plus 0. Then 5 times minus 1, that is minus 5. The next one, we use the first row against the second row against the second column here. So 3 times 3 gives you 9. 0 times 0 gives you 0. 5 times 4 gives you 20. All right. I'm breaking it down here so that it's very clear. So minus 2 minus 2 minus 4 is minus 8. 6 plus 0 plus 16, that gives us 22. Minus 3 minus 5 gives us minus 8. And 9 plus 20 gives us 29. Now we got 2 by 2 as we expect. And the next thing to do here, is to now add the products to D. So AB plus D now gives, AB is gotten to be minus 8, 22, minus 8, 29. And then we add it to D rather, which is minus 4, 2, 3, and 1. So we do the entry-wise also. Minus 8 minus 4 gives us minus 12. 22 plus 2 gives us 24. Minus 8 plus 3 gives minus 5. 29 plus 1 gives 30. That becomes AB plus D. All right, so the next thing to do now is to think about C times A transpose. So let's go into C times A transpose. So question C is to think about C times A transpose. We need to check the compatibility rule as well. Remember that size of C is 3 by 3. The size of A was 2 by 3. So A transpose, the size will be 3 by 2. So the question would be, can I multiply C by A transpose? Which would mean I'm multiplying a 3 by 3 matrix by a 3 by 2 matrix. The answer is yes, we can do this multiplication. Remember, the columns here, the number of columns in C is the number of rows in A transpose. So the product will be 3 by 2. All right, so once we know that is possible, we already know how to find A transpose. So A, again, let's recall who is A. A is 2 minus 1, 4, 3, 0, 5, which means if we do the same thing as we did with B, A transpose will be take the row for column. So that would be 2 minus 1, 4, and the second row here as the second column here. So that would be 3, 0, 5. All right, now that I have A transpose, I can multiply C by A transpose, which is, so C again, let's recall, is 1, 0, 4, 2, 1, 3, minus 1, 2, 0. I'm multiplying it with A transpose, which is 2 minus 1, 4, 3, 0, 5. And now, carefully again, I'm going to take the first row, multiply the first column here, and also the second column. So again, 1 times 2 is 2. I'm just going to do it by the side here. It's a rough estimate somewhere here. So 1 times 2 is 2. 0 times minus 1 is 0. 4 times 4 is 16. So 2 plus 0 plus 16 is 18. So the first one is 18. I go to the next column. So 1 times 3 will be 3. 0 times 0 will be 0. 4 times 5 will be 20. So 3 plus 20 is 23. Move to the next row. I do the same multiplication with the two columns. So again, 2 times 2 is 4. Plus 1 times minus 1 is minus 1. So just going to, it's minus 1. And then 3 times 4 is 12, plus 12. So 4 minus 1 is 3. 3 plus 12 is 15. So I have 15 here. So I go again. 2 times 3 is 6. 1 times 0 is 0. 3 times 5 is 15. 6 plus 15 is 21. So I'm done with that. Then I move to the next row. I use this row again to multiply each of the column in the next in the other matrix. So minus 1 times 2 is minus 2. 2 times minus 1 is minus 2. And 0 times 4 is 0. So minus 2 minus 2 and 0, that would be minus 4. And lastly, I'm going to have minus 1 times 3, which is minus 3. 2 times 0, which is 0. 0 times 5, which is 0. So adding them together will be minus 3. And that becomes our answer. So C times A transpose is 18, 23, 15, 21, minus 4, and minus 3. All right, so we go now to the last question. That says C times B plus A transpose. Again, we just need to check the compatibility. So let's see. C is 3 by 3. B is 3 by 2. So it makes sense to multiply C by B because these agrees. The columns, the number of columns of C is exactly the number of columns in B. All right, and when we do the multiplication, C times B, we should expect these guys, which is 3 by 2. Now, previously we saw that A transpose, the size of A transpose is going to be 3 by 2. So it makes sense to add C times B to A transpose because they have the same size. All right, again, let's quickly do C times B, which will be C again is 104, 2 minus 3, sorry, 2, 1, and 3 minus 1, 2, 0. All right, times B. B is minus 1, 2, minus 1, 3, 0, 4. All right, I'm going to walk through this very quickly, just as we have done. So 1 times minus 1 times minus 1 gives us minus 1. 0 times 2 gives 0. 4 times minus 1 gives minus 4. So minus 1 minus 4 gives minus 5. I'm going to go to the next one. 1 times 3. So what I'm doing again is to take the first row here and multiply with the columns here and then the columns here. So I just finished with the first one. The second one is 1 times 3, which is 3. 0 times 0, which is 0. 4 times 4, which is 16. If I add everything together, I'm going to get 19. So let's go to the second row. So 2 times minus 1 is minus 2. 1 times 2 is 2. 3 times minus 3, minus 1 is minus 3. So minus 2 plus 2 minus 3. That will be minus 3. And then 2 times 3 is 6. 1 times 0 is 0. 3 times 4 is 12. 6 plus 12 is 18. All right, so I go to the last row. Minus 1 times minus 1 is 1. 2 times 2 is 4. 0 times minus 1 is 0. So 1 plus 4 is 5. Last one will be minus 1 times 3 is minus 3. 2 times 0 is 0. 0 times 4 is 0. So the answer will be minus 3. That becomes C times B. Now let's add it to A transpose. So CB plus A transpose will be, now the result we got for C times B is minus 5, 19, minus 3, 18, 5, minus 3. If I add this up, I'm going to add it to A transpose, which we've obtained before, which is 2, 3, minus 1, 0, and 4, 5. Again, I'm going to add entry-wise. So minus 5 plus 3 is minus 3. 19 plus 3 is 22. Minus 3 minus 1 is minus 4. 18 plus 0 is 18. 5 plus 4 is 9. Minus 3 plus 5 is 2. And that is the final answer. So I hope that I'm able to cover almost everything that is needed to do matrix algebra. I have other slides here which are basically what I created to see that we could have enough space to do the computation. In my next video, I'm going to talk about inverse of a matrix, and the goal is to start from the idea of a 2x2 matrix and then develop how we can go into finding inverse of any size of the matrix. I hope you enjoyed the video. You could leave some comments and watch out for my next video. Thank you very much.